Here's the equation where the I appears. This is the Schrodinger's equation for quantum mechanics. I'm not going to go into a lot of detail, but note it's a partial derivative, the second partial derivative of what's called the function of space and time. And note what it's equal to, and got some interesting parameters there. H is Planck's constant, and there's our famous I, square root -1, involved in Schrodinger's famous equation. That's the miracle that Huygens Wigner could not explain. Now, I could spend some time going through that derivation, but it'll take us about 4 weeks to walk through it. So excuse me for doing that. Okay. Also going back to the fall of the moon, inverse square law. How many know about Coulomb's law in electricity? It's the same law involving the attraction and repel action of in electricity. So two different entities, gravitation and electricity, have the inverse square law involved in their very foundation. That's another question that is not answerable. Why this relationship, and why this relationship when it's a very simple relationship also. So note very carefully, and coming back to Schrodinger's equation, that looking at the history, mathematicians just chose a simple way of convenience. We don't know how to figure out square roots of negative numbers. Let I be the square root of -1, work with the math, and guess what we get as a result. And so that's a very important thing that mathematicians do sometimes. They work with convenience. That's part of their commitment to simplicity and beauty. Although you wouldn't think this is simple. Yeah, that's a little complex, and it does get complex. So, and again, Wigner says this imaginary number is necessary not only in quantum mechanics, but also, as I've mentioned, in the theory of electricity and the infinite wonders of fractal geometry. So this mathematical object of convenience has achieved far more than its original design. Far more. So given this fact, Wigner responds with the amazing remark, "It is difficult to avoid the impression that a miracle confronts us here." Finally, he concludes, "Fundamentally, we do not know why our theories work so well." And then he says this, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning." But all these equations I've given you examples of are really descriptions that are used to predict things and confirm things. What's amazing about the 20th century, and I'm only going to give you about a couple examples, 19th and 20th century, is that they contain a host of examples where mathematical derivations resulted in the discovery of realities hitherto unknown. What we see happening has been an astonishingly successful strategy employed by scientists who use the corpus of mathematical concepts. In other words, mathematical structures are intimately connected with all aspects of the workings of the physical world. And here's the quote again from Jerry B. King. I promised I would give you some more of his words. He starts by saying this, and we've heard the word miracle, mystery, bizarre. Well, here's another one for us. Now we come to something really spooky. The applied mathematics process works. And then he goes and looks at Wigner's analysis. And then he concludes, based upon Wigner's analysis, he says, "The miracle itself is wonder enough." Yes, I agree with that. But if, as I claim, the motivation for the development of mathematics is primarily aesthetic and not utilitarian, then the wonder compounds itself. We are talking about the paradox of the utility of beauty, and we are dealing with a miracle of the second order of magnitude. Just, let that one sink. Just looking for beauty, and then these applications come up. Theoretical physicist Stephen Weinberg says this: it is positively spooky, there's the word again, how the physicist finds the mathematician has been there before him or her. The physicist is working away, okay, and the mathematician says, okay, I don't know, okay, here's this, right over here. This will help you right there. Theoretical physicist and mathematician Freeman Dyson says this: one factor that has remained constant through all the twists and turns of the history of physical science is the decisive importance of the mathematical imagination. And in physicist Richard Feynman, we all know about him, 20th century, I find it quite amazing that it is possible to predict what will happen by mathematics, which is simply following rules which really have nothing to do with the original thing. Here's two examples. The first example is, I'm going to show them to you. I'm not going to explain a lot about it, but I'm going to show you these. These are called Maxwell's equations. Now, I talk about some interesting equations here. Now, he developed these. They were structured in this way later after his death. Maxwell is a very interesting man, 19th century, James Clerk Maxwell. He had engraved over the Cavendish Physics Laboratory in Cambridge University, this is still there, a quote from Psalm 111, verse 2. Great are the works of the Lord, pondered by those who delight in them. That's over the laboratory. Now that's wonderful. That's science, biblical Christian science in a nutshell. We investigate the works of the Lord because they bring us such pleasure as the results that we discover. Kepler could have said the same thing. In fact, when Kepler discovered the three laws of planetary motion, in fact, the first one on the elliptical motion of planets, he couldn't quite get the data to fit circles, and he then used the ellipse. Of course, that's an ancient Greek invention. 2000, back in 600, 500 BC, we're talking about Kepler, 17th century. Over 2,000 years before, all this stuff was already worked out, and Kepler says, what about the ellipse? And he looked at the planet Mars, was his conundrum, and he saw that the data fit if I assume that the planet Mars rotates around the sun in an elliptical fashion. And he worked on that for 8 years. I mean, before computers, we still have some remaining work of his actual arithmetic, page after page after page. I think we have about 1,000 pages of his actual handwritten arithmetic. So after 8 years, you'd think after you figured it out finally, you saw everything work, what would you do? What would be your response? Right? You know what he did? By his own confession. He fell to his knees and raised his hands. Said, my God, I am thinking thy thoughts after thee. That was his response. And James Clerk Maxwell will be a man of the same mindset. So his equations, basically tying electricity to magnetism, electromagnetic theory. And what he did is that he predicted the existence of electromagnetic waves before they were ever discovered. And that's the last equation right here, this conjecture. Let's see if I can read it. Electric current produces a magnetic field. And then you've got some other explanations there. Don't worry about the explanations. I just want you to see the equations. And again, we're looking at some interesting symbols there. Closed integral, that's integrating over a closed curve. That's what that little integral sign with the circle there. And a lot of other things I could define, but I don't have the time. But when mathematicians look at this, you may look at this and say, huh? When a mathematician, when Maxwell saw these equations, he said, this is beautiful. In fact, it's been said that Maxwell's theory is Maxwell's equations. Maxwell's theory of electromagnetic waves is Maxwell's equations. So he conjectured the existence of electromagnetic waves. Heinrich Hertz, the Hertz unit is named after him, discovered the existence of radio waves in space, and he verified all of Maxwell's equations and his ensuing predictions. Heinrich Hertz said this in response to Maxwell's equations and his discovery. One cannot escape the feeling that these mathematical formulas, take a look at them, have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. Richard Feynman said the same thing. More comes out than goes in. More comes out than goes in. That's the first example. The second one I don't have a slide on, but it's the famous Dirac's equation. Paul A.M. Dirac lived from 1902 to 1984. In 1928, he, quote-unquote, discovered the positron and antimatter via a deep-level method of mathematics that involves factoring an equation. Now, I don't have the equation up there for you, but I can tell you where to get it to look at it. That equation that he factored, we all know about factoring equations. It's a little more in detail than that. It was called the Klein-Gordon equation. He used a special algebraic factoring technique that had been developed about 70 years before by a mathematician by the name of Clifford. It's now known as Clifford algebra. So he actually invented Clifford's algebra to factor this equation, and then found out later that Clifford had already done that 70 years before. And when he factored the equation, to make a long story short, he was forced from the mathematical equation, the derivation that resulted, to predict a new type of matter called a positron. I'm saying a lot in one sentence. This particle, the positron, was discovered experimentally in 1932 by Carl Anderson. So mathematics, what was mathematically possible, was eventually realized to be physically possible. Those are just two examples. You can multiply them many, many times of mathematical discoveries predicting something that would exist, and later it was found to actually experimentally exist. Now, naturalism is glaring silence in all of this. Remember, naturalism, from the very word itself, is a nature-first worldview. It's a worldview that's also impersonal. Matter is all that there is. We all know about Carl Sagan's famous quote, "The cosmos is all that is and all that will be, and all that has been." Naturalism cannot justify Dirac's formalist derivation. This, again, was another algebraic convenience with no view in mind for a real-world application, with the resulting genuine and totally unsuspected physical insight. Now, this is equivalent to, if you embrace naturalism, it's equivalent to having this happen, okay? Let's play a game of chess. It yields some insight into the structure of the atom. You actually could come to that conclusion assuming a naturalistic, probabilistic world. Or the study of palindromic numbers. You know what a palindromic number is? A number that is read, if you read the digits of a number from left to right, like 8118, and go from right to left, 8118, that's a palindromic number. So if you study, they're really fascinating to study. Also, there are words, English words that are palindromic. It's equivalent to the study of palindromic numbers predicting the boiling point of water. I mean, it's just like throw the dice. Excuse me. I lost by throwing my dice. My sound okay? Okay. So you really cannot justify it. It's glaringly silent. And then there's a beauty here that's deeper than anyone could ever have expected. And I'll give you a few quotes on this. Physicist Roger Penrose says this about the applicability of mathematics in physics. He characterizes that applicability as a profound interplay between the workings of the natural world and the laws of sensitivity of thought. An interplay which, as knowledge and understanding increase, must surely ultimately reveal a yet deeper interdependence of one upon the other. British physicist Norman Campbell says this: math equations reflect, in terms of how they apply to physics, the marvelous power of pure thought, aiming only at the satisfaction of intellectual desires, beauty, order, symmetry, to control the external world. According to Dirac, the mathematician has been for millennia using his powers of ingenuity to develop fundamental physical laws in terms of a mathematical theory of great beauty and power. And then Richard Feynman says this: every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. Why? I have not the slightest idea. To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of nature that is revealed by studying mathematics. And Feynman caught it in his writings, but he could not explain again why. So here are the questions. How can facts about immaterial objects, derivations of mathematics made by the minds of mathematicians, have any relevance to the universe we inhabit? What can account for the application of mathematical theory to the physical world? How can it be that the mind and mathematical objects derived in the mind connect to realities outside the mind? Einstein spoke of a quote-unquote religious awe in the face of the openness between human knowing and the structure of the universe. It almost led him to worship, except he wasn't worshiping the God of Scripture, but he was led to this wonder and awe, which is really deep inside many, many mathematicians and scientists, believers and unbelievers alike, except the believers know where to focus their worship. They know who to focus it upon. So why does mathematics work? In naturalism, humans are presupposed to be the product of undirected processes occurring in natural history. There is no reason, therefore, for any connection between the human mathematical thinking and natural world revelations. As we said, naturalism is a nature-first, impersonal worldview. Compare that to biblical Christianity. We read in Scripture, in the beginning God created the heavens and the earth. We also read in Scripture, in the beginning was the Word, and the Word was with God, and the Word was God, and all things were made by the Word. And we also read in Scripture, Colossians chapter 1, paraphrasing from J.B. Phillips' translation, Christ is the first principle and the upholding principle of the whole scheme of creation. Colossians 1:15. So biblical Christianity, as a worldview that's totally opposite to naturalism, it's a logos first. The Greek word for word is logos. Of course, the ancient Greeks understood logos as the rational order and harmony of the world, but that was inherent in nature. The Apostle John took the word logos and put it into its right context. The logos is the personal God-man, in whom and by whom all things were created, and in whom and by whom all things consist and cohere. So biblical Christianity is a logos-first, personal worldview. Christ is the true source of rationality of the universe, the rationality outside of man, and the rationality inside of man. In the biblical Christian worldview, God designed a quote-unquote user-friendly creation where the world of human thought mirrors the deep structure of the world. God's world is user-friendly, where we humans are the user, and where the tool of discovery that renders the physical world friendly is mathematics. In the 20th century, early 20th century, the founders of quantum mechanics spoke of a correspondence principle relating classical to quantum mechanics. This correspondence principle is much deeper than any of these scientists could ever imagine. The true correspondence is between the human brain, mathematics, and the physical world as a whole. As I've stated repeatedly, the universe is user-friendly, and this is the challenge to naturalism. And the challenge is answerable only by embracing the biblical Christian doctrine of creation. The mind of man, with its mathematical capabilities, and the physical world, with its observable mathematical order, cohere, connect, correlate, because of a common creator. Einstein's eternal mystery has a solution. The biblical revelation of the Creator God is the unifying factor that reconciles what is irreconcilable in the naturalistic context. Thank you.
Thank you very much. And we're going to have a period of questions and answers. But first, start passing around a plate. like to take an offering to help defray the costs of bringing in good speakers, like Mr. Nickel. Isn't it interesting to listen to somebody who has some excitement about what he talks about? I remember myself, I had a math minor when I was in college, and I had a professor that was like this. And you make me remember him, because he would get up. He never did it until you got past calculus, but once you got into the other derivative forms of math, he would get up and almost dance across the front of the classroom, with the expression, why do I love mathematics? What is it about mathematics that is so great? It's that it's beautiful, that it's synchronous, that it works. And he says we can do so much with math that we have no idea what the application is, but we know that eventually we'll figure it out, because nothing comes by chance. So it was a very interesting experience. Does anybody have any questions? Yeah.
If I can't answer them, I'll refer you to Einstein.
40 years ago, when I studied physics, they taught me that there are certain things known as constants. For example, you mentioned the Planck's constant. Today, you can find on Google the Planck's constant is not constant. I don't get it. Then the other one is the probability of amino acids self-assembling to make a protein is less than 1 raised to the power of minus 100. So can you elaborate on this, please?
What was the last one again?
The probability of amino acids self-assembling to become proteins is improbable.
1 over 10 to the power of what?
I think it was somewhere around 40 or something. No.
Yeah. Actually, I've read in another context of the arrangement of, I think it's the way the solar system is coordinated. The probability is 1 over 10 to the power of 123. You know what a Google is? It's 10 to the power of 100. So that's, virtually 0. I don't have an answer to Planck's constant. Sorry. But yeah, I would agree with the even with 15 billion years, as the evolutionist says, that we've been on, the universe has existed since the Big Bang, that probability is still impossible. Sorry, I can't answer Planck's constant.
I have a comment and a question. The comment is, I was really drawn to your statement about how the discovery of I, the imaginary number, accomplished far more than its original design. And I thought that was so cool, because that's parallel to the way a real scientific theory works, is that a scientific theory is developed. Once it's been developed, it predicts things that nobody ever imagined it might predict. Like the special theory of relativity predicted E equals mc squared, for instance. But every real scientific theory does that, and it stands in such stark contrast to what evolutionary theory does. And I thought that your comment about the discovery of I is kind of that theory in a microcosm effect, where I had such far-reaching and unexpected consequences. My question is referring back to where you're talking about how mathematics is really based on the beauty of things. People are really looking for the beauty, and which consists of symmetries and interesting connections between different logical things. I became aware several years ago of a device called the E8 symmetry group, which they've been exploring as part of, an extension of string theory or some mega theory like that. I have very little understanding of it, and I was wondering if perhaps you might know enough that you could elaborate, so that we could understand it maybe a little better.
I'm going to have to say no on that one, too. Sorry. But, you know, what's going on? My comment about all the activity with the math and things like that. See, my point in what I was saying today or tonight was basically to show you that the human mind has been wired by God to think a certain way. And the way in which we think in terms of mathematics does correlate to the real world. We may not know how it does initially because beauty is driving this, and so mathematicians just do it because it's beautiful. All these wonderful connections. I've had so many connections, not by my own inventions or discoveries, but by seeing the other discoveries that mathematicians have made. I'm not original at all. But when I see a Kepler bowing his knees and saying, you know, my God, I'm thinking thy thoughts after thee, when he's doing mathematics, just think how God would bless the world in the future if we had Christian scientists and mathematicians consciously doing that. Do you think God would reveal, like he revealed the secrets of the peanut to George Washington Carver? He certainly would reveal the secrets of creation. We haven't uncovered it all. And your comment is one example. And of course, I'm not omniscient as a mathematician. You try to understand everything about mathematics, you can't do it. The last person who did it was Carl Friedrich Gauss. After that, everyone's limited. But you see the passion there if we make a connection to fearing God in our science and math and our education work. And it really does drive a blessing, I believe, that God will give in the future. Next.
Sir, just a simple question. Does the Earth rotate clockwise or counterclockwise?
Astrophysicist. Bill.
I didn't hear you.
I know that the drains in the southern hemisphere go opposite to the drains in the northern hemisphere. And also when you turn I lived in Australia for 6 years, when you turn the door handles indoors in Australia, you have to turn them the other way. Of course, I always get confused between counterclockwise and clockwise, so I have to look at my clock. I didn't ask the question. Does anyone know? I don't know offhand. Yeah, it depends on your perspective.
Yes. I've seen publications where I've seen it in movies and it's actually going counterclockwise. I'm saying, wow, this doesn't make any sense.
Yeah.
I don't know. It's very
I think when I was talking to Bill, the Galileo spacecraft that forgot, it was the Galileo spacecraft that got out and turned back and looked at the Earth and did time-lapse photography and actually showed its rotation around its axis. I remember it was going. Okay, how was that? Counterclockwise. Yeah, if I remember that. Yeah.
Counterclockwise if you're looking down from the north.
Yeah. Right. Because I was trying to look at it from I was looking down. Yeah. So if you're from the southern hemisphere, it goes the other way.
Yeah, I was speaking to you earlier before the session began about astronomical theories and cosmology and how it's in such chaos right now. Virtually every major theorem that has been put forth over the last 20 years has come under attack and has been disproven some way or another, from the Big Bang to just about all the rest of them. And after listening to your presentation, I believe the reason for that is because they start with conclusions and try to force the math to support their conclusions rather than following the beauty of the mathematics that have already been well established.
Yeah. That sometimes happens.
Yeah, and the other thing I wanted to mention was something that I studied 30, 40 years ago. When NASA decided to go to the moon, they were trying to determine how best to get something from Earth to the moon with the minimum amount of energy. And the final solution came down to the mathematics worked out by a German mathematician in 1920 by the name of Hermann Hoffmann. And his mathematics gave them the way to get from any celestial body to any other celestial body with the minimum amount of energy. 80 years before it ever was really put to use.
And he never thought of that
significant
being
use.
an application. I'm sure he did. Yeah. there's a wonder in tying your study of math and your work in math. If you tie it to a conscious commitment to application, you might be a step ahead in terms of deriving things that are applicable. Anyway.
Now, seems to me that all the number systems of all the world is based on 10, and we happen to have 10 fingers. If we had 8 fingers, like cartoon characters, would it have changed our math?
No.
Would we still be based on 10?
Oh, well, you could, any base will work. I mean, base 8, base 2, choose any base you want to. You can make everything works out, all the rules work out. So we're just accustomed to base 10, thanks to the Hindus and the Arabs for that.
Would an application of what you've presented tonight be the theoretical consideration that black holes would exist before there was observational evidence that they may exist, and so the mathematicians thought, hey, this is possible that this could happen, and then God being the creator, he also thought, this is possible, this would be fun to do.
Yeah, that's possible. Of course, black holes are a controversy in some quarters, too.
Sure.
You know, it's hard to do experimentation just by looking at spectroscopy. I didn't say that right. Spectrum analysis. That's what all you're dependent upon. So again, lots of things are read into what you are looking at.
Okay.
Next.
I know there's many different areas of mathematics, from differential equations, based in calculus, algebra. Which one do you think has had the largest impact in the mathematical community?
In what era?
That's affecting us now. Let's go
Now?
in modern community.
There's a lot of work done in structure analysis, which would be called number theory, or abstract algebra, as I mentioned, fields, groups, and rings. A lot of that has some amazing applications in physics, unsuspected. But again, you'd have to do a survey of a lot of cutting-edge mathematicians, which I'm not aware of. A lot of that, what's going on.
I have a question for you, James. Why is the universe so linear? The same second-order linear differential equation describes almost every physical process you look at. The simple harmonic oscillator, so it applies in springs and masses and inductors and electricity. Everywhere you go, it applies. Why is that?
I think it's a part of God's wisdom to keep things simple. Yeah, and of course it's advanced to try to do the differential equations and to work with them. But when you understand what's going on, I remember I was taught differential equations. I was bored stiff to it. There was no connection whatsoever to anything until I started to do studying on differential geometry and said, whoa, look at this. Why wasn't I taught this? And so, yeah, it's just like when you look at quadratic equations, it's the same thing. Why are those so applicable to motion on the Earth? Parabolas and hyperbolas and ellipses, and they're all quadratics. So it's just there are basic, simple foundations that govern everything. And then you add on to that to make other discoveries. I think it's just God's choice to be. There's a treasure in creation. I like the scripture in Proverbs 25, verse 1. So it's the glory of God to conceal a matter, glory of kings to discover a matter. So when you discover something about differential equations being linear, what's your response? Your response is, wow, wonder, yeah, cool. And of course that's designed that way by God to make our response directed toward him, which fulfills our destiny as worshiping creatures. So it's a gift from him. I wish I was taught that when I went to university. I walked out of university vowing never to open another math book because I didn't have one of those exciting professors. They were all just about as boring as could be, droning up there and doing their blackboard work from start to finish without saying a word. So there's your lesson for today, and walk out.
if you start with Christ as the first principle, what steps would you take, or have you worked this out, to get from Christ as the first principle to the very elemental principles of mathematics?
The elemental principles of mathematics it has to embrace a doctrine of unity and diversity. You got to have unity and diversity to understand 1 + 1 = 2. You have to have unity and diversity to understand 1, 2, 3, 4 counting. And counting, I've written a book called, I'm not sure what to entitle it. It's not ready to be published. It's called The Foundations of Mathematics. And I start with counting, and I show how from counting you can get directly to calculus. And of course, from calculus you get directly to everything, almost everything else. And so counting is really the foundation for all of mathematics. So what's the foundation of counting? You have to embrace a philosophy of unity and diversity. For example, if I count how many individuals here are in this room, I'm counting 1, 2, 3. And so 3 is attached to a unique university. 3 is a unique person right here. Okay, so 3 is an abstract concept, so it's a unity. And so I'm attaching it to you right there. You're the third person I've counted. Here's my third finger. So I've got a diversity between 3 fingers and the third person I've counted. That's very simply what I mean by unity and diversity. There's only one philosophy that has an adequate philosophy of unity and diversity. Guess what it is?
Christ.
Well, it's the doctrine of the Trinity, and Christ is the foundation. 3 in 1. Either you'll go off in one area, you'll absolutize unity. You know what I mean by absolutize unity? When you make unity the one way to investigate everything that exists, all is one, all diversity is an illusion. The Hindus embrace that. And so they would say to you, if they want to be consistent, if I punched a Hindu in the nose and created a bleeding nose, he would say that blood's an illusion. It doesn't really exist. If he wanted to be consistent with his what we call monistic philosophy. On the other hand, you have absolutization of diversity. Everything is diverse, and there's no unity governing diversity. You really can't do mathematics without that. You can't do any theorems. You can't do any formulas, any laws, without a unity governing all the diversity of experiences. So you've got to have both unity and diversity. And there's only one philosophy that undergirds that, and my book kind of goes through all that in great detail. So I think that's what I would say. When I haven't talked about a very famous theorem that was developed by Kurt Gödel in the 1930s called the incompleteness theorems. It basically said that there are things in mathematics that you cannot prove logically and deductively. Even things in terms of the counting numbers, the arithmetic of counting numbers, there are what mathematicians believe something that they believe a principle would be true, but they can't prove it deductively. Well, Kurt Gödel says that's going to happen with mathematics. You have to look outside your logic. You have to look outside mathematics to really develop and find the true foundation for it. And so I say, well, Christ is the foundation. Now, that's my theory of everything TOE. Now, that doesn't mean that those who are working on TOE should stop. We can always refine our physics also, because we had comment about physics is up in the air, cosmology, we're not really sure about this. Well, we're always refining things. Newton's theory was refined by Einstein. Einstein is going to be refined. So you're never going to get an absolute theory of everything that's going to explain everything totally without any, full stop at the end, as they say in Australia, period. We're done. No more need for discovery. It's never going to happen, according to Gödel's theorem, and also according to biblical Christianity. There's treasures in creation. We'll never be able to unearth them all. Does that kind of help? Did you follow the unity and diversity line, sort of? Anyhow, read my book. It'll be explained more thoroughly.
Get the book. Okay, well, let's thank Jim again.
Okay. Also going back to the to the fall of the moon, inverse square law. How many know about Coulomb's law in electricity? It's the same law involving the attraction and repel action of in electricity. So two different entities, gravitation and electricity, have the inverse square law involved in their very foundation. That's another question that is not answerable. Why this relationship, and why this relationship when it's a very simple relationship also. So note very carefully, and coming back to Schrodinger's equation, that looking at the history, mathematicians just chose a simple way of convenience. We don't know how to figure out well. And then he says this: the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. But all these equations I've given you examples of are really descriptions that are used to predict things and confirm things. What's amazing about the 20th century, and I'm only going to give you about a couple examples, 19th and 20th century, is that they contain a host of examples where mathematical derivations resulted in the discovery of realities hitherto unknown. What we see happening has been an astonishingly successful strategy employed by scientists who use the corpus of mathematical concepts. Here's the equation where the I appears. This is the Schrodinger's equation for quantum mechanics. I'm not going to go into a lot of detail, but note it's a partial derivative, the second partial derivative of what's called the function of space and time. And note what it's equal to, and got some interesting parameters there. H is Planck's constant, and there's our famous I, square root -1, involved in Schrodinger's famous equation. That's the miracle that Huygens Wigner could not explain. Now, I could spend some time going through that derivation, but it'll take us about 4 weeks to walk through it. So excuse me for doing that. Square roots of negative numbers. Let I be the square root of -1. Work with the math, and guess what we get as a result. And so that's a very important thing that mathematicians do sometimes. They work with convenience. That's part of their commitment to simplicity and beauty. Although you wouldn't think this is simple. Yeah, that's a little complex, and it does get complex. So, and again, Wigner says this imaginary number is necessary not only in quantum mechanics, but also, as I've mentioned, in the theory of electricity and the infinite wonders of fractal geometry. So this mathematical object of convenience has achieved far more than its original design. Far more. So given this fact, Wigner responds with the amazing remark: it is difficult to avoid the impression that a miracle confronts us here. Finally, he concludes, fundamentally, we do not know why our theories work so well. In other words, mathematical structures are intimately connected with all aspects of the workings of the physical world. And here's the quote again from Jerry B. King. I promised I would give you some more of his words. He starts by saying this, and we've heard the word miracle, mystery, bizarre. Well, here's another one for us. Now we come to something really spooky. The applied mathematics process works. And then he goes and looks at Wigner's analysis. And then he concludes, based upon Wigner's analysis, he says, the miracle itself is wonder enough. Yes, I agree with that. But if, as I claim, the motivation for the development of mathematics is primarily aesthetic and not utilitarian, then the wonder compounds itself.